Now, you may have intuitive understanding of logistic regression. Next, let's dive into mathematical understanding. But before diving into details, first, let's obtain overview. Mathematically, logistic regression can be explained using these components. First, the logistic function transforms any real-valued number into a value between 0 and 1, making it suitable for estimating probabilities in a binary classification setting. As a model representation, logistic regression models the probability of an observation belonging to the positive class, usually labeled as 1. Here, the model is a function of the input variables using a logistic function. The decision boundary is a threshold value separating observation into positive and negative classes. In parameter estimation, we aim to find the optimal parameter values in logistic regression so that the model achieves the highest possible predictive performance. To find optimal parameters, we use the log likelihood and optimization algorithms. To interpret the results, we use coefficients in logistic regression to quantify the impact of predictor variables on the outcome. In model evaluation, we use various performance metrics to evaluate the model's predictive performance. Let's see each component one by one. But this chapter provides only overview, so it is okay for us to obtain rough understanding. Detailed explanation of each component will be provided in later chapters. The core of logistic regression is the logistic function, often referred to as the sigmoid function. This function maps any real valued number into a value between 0 and 1, making it suitable for estimating probabilities. The logistic function is defined by this equation. Here, sigma z is the output of the logistic function. Z is the input to the function. E is the base of the natural logarithm. In logistic regression, we model the probability that a given input x belongs to the default class, usually class 1. This probability can be written by this equation. Here, y is the binary target variable. x1, x2, xn are the predictor variables. Beta 0, beta 1, beta n are the parameters of the model, with beta 0 being the intercept term. The decision boundary in logistic regression is a property that decides which class a new data point should belong to. It is defined by setting the logistic function to 0.5. If the probability of y equal to 1 given x is greater than 0.5, the model predicts class 1. Otherwise, it predicts class 0. The parameters beta of the logistic regression model are usually estimated using maximum likelihood estimation. The likelihood function in logistic regression is given by this formula. Here, yi and xi are the observed values for the ith observation. Maximum likelihood estimation aims to find the values of beta that maximize this likelihood function. In practice, it is more convenient to maximize the log of the likelihood function, that is, log likelihood, given by this formula. The optimization of the log likelihood is typically performed using numerical methods like gradient descent, because there is no closed-form solution for the maximum likelihood estimates of beta. The goal of logistic regression is to estimate the probability of an event occurring. This probability can be expressed by this formula. This formula derives from odds and log odds. The exponent of E in the denominator is a linear equation consisting of the predictor variables xi and their respective coefficients beta I. Each coefficient represents the direction and magnitude of the influence of the corresponding predictor variable, respectively. When the coefficients are positive, the larger the predictor variable, the higher the probability that the event will occur. When the coefficient is negative, the larger the predictor variable, the lower the probability that the event will occur. When the coefficient is zero, changes in that predictor variable have no effect on the probability of the event occurring. The absolute value of the coefficient then represents the impact of the predictor variable on the probability of the event occurring. The larger the absolute value of a predictor variable, the greater the impact that the predictor variable has on the probability of occurrence. Logistic regression models are evaluated using metrics like accuracy, confusion matrix, AUC score, etc. These metrics will be discussed in detail in later chapters.